Hello, everybody. So today I'm giving my RCMAR annual meeting completed works talk, and this talks about showing if our phenotyping algorithms fair for underrepresented minorities within older adults, and we'll go through uh, the process of determining this. So why is this work important? Well, we all seen that there's been this influx of research showing that there's all this racial bias in AI systems, or any tool that basically has a machine learning model behind them. So there's been books about it. There's been many books about it, and big technology review articles that so this is getting more mainstream. So the main ideas behind this work is that we assume, based on previous work by a lot of other people, that machine learning models are biased most of the time, and hence probabilistic phenotype models should also reflect this. Why? Well, because they're built on machine learning models and on real world data. So here we want to create a methodology that could be used in the following settings, at least for healthcare purposes. We want to use it in a standard common data model, so it could be ported. It needs to be fully reproducible. It's part of an R package that does all of this, because we want to share the code and run everywhere, and fully transparent and configurable, meaning that there's accountability at every step of what's being put in here and how it's being executed. So here, just a kind of a big disclaimer. We're not trying to find the best performing phenotyping algorithms in this work. We're trying to see if these models are fair to underrepresented minorities within older adults. And we're going to present some ideas on how to fix them. So the phenotype methodology we're using, it's probabilistic, it's not rule based. So here, this is via noisy labeling, which is using this Aphrodite package available for the Odyssey community that runs on the OMUP common data model. So we use Stanford Healthcare's data, around 3 million patients over a longitudinal period of years, of probably 20 years or so. And here you can already start, so our phenotypes that we selected were dementia, frailty, mild cognitive impairment, Alzheimer's disease, and Parkinson's disease. And here, when you see the breakdown of, the race breakdown, you can already start seeing the very different, different, ranges of these ones, right? So you have some races that where the data is only 11%, all the way down to 0.2% for Native Americans, meaning that all other races are not very well represented, right? So the majority of people in this data set is white. And also you see that there's around 23% of data for each phenotype that it's unknown patients. So those people are going to be removed because you can't really ascertain what race they have, and we're not going to be doing any imputation. We're just going to go with the self-reported race for this study. So evaluation matrix, so we're going to have the typical precision, recall, and accuracy metrics that you see in all the machine learning models, but we're also going to focus more on variation. And here, variation is basically, we want to see how different the model performance is between, a set of comparisons that we're going to present. Why? Because we want to know if the model, how much does it vary when we do different experiments. So the approaches that we're evaluating, it's we're going to build models for individual races and compare across them. That's one approach that people usually propose, or it has been mentioned in literature. And also the second approach we're going to do, which is a more traditional one, is that we're going to balance our models and do sort of a leave one out evaluation to see how each racial group contributes to the models. So here we have our 4 phenotypes, and we're looking at the accuracy, across the phenotypes. So as you can see in this charts, or in this, tables actually, the less red that the table is, it means the better, right? Why? Because a higher red color means that there's a higher variation between the models. And here what we're comparing, if you look at the top left corner, where we're comparing in the dementia models. So basically, we're comparing, a model built, only on Asian patients and how it performs across all other, races as determined by the race flags on the OMOP CDM. And then we have the comparison of, a model built only on white patients and how it performs against, all the other races. So if you notice the diagonal, it's going to be zero because, you don't compare the model against itself because that's the racial group that was built on. So here for dementia, if you notice that the variation doesn't change that much, meaning that, a model that's built on Asians performs equally the same, when you have patients uh, of other races. And this is an interesting finding, and we'll generalize it a little bit later. And the same thing happens for the Alzheimer's disease model. We don't have any variation, higher than 10%. So there's nothing extremely red. But you also see that, for example, for mild cognitive impairment, you have that the model varies all the way up to 25% in performance. And this is striking to see because, well, if your model performs at 75% accuracy and you have a loss of 25% accuracy, you're back to 50%, which is, basically just flipping coins, picking, the people for that phenotype. So that's really bad. So as you can see, lower variation here is more important and also shows, how the racial distribution contributes to this. So in this approach, we notice that small racial representation. And this is something that we've seen on the earlier slide. There's people with very little, a small set of patients. So this leads to non-generalizable results. That's usually when those models turn pretty red. Those figures there, and also the phenotype complexity plays a considerable role, and we're gonna see that a little bit more later. So if you can see now we're using the leave one out balanced model building performance. So for full models and balanced models, those are the traditional type of models that are built in literature, phenotyping literature. And we see that, for dementia, again, the phenotype that was pretty stable in our individual race comparison is also pretty stable for full model and balanced model. We see the same thing for Alzheimer's disease. And where you're doing the leave one out comparisons, obviously, when you leave one out, white race, which was most of the data, you start getting this big, accuracy performance swings or variation between models. So that's to be expected because you're basically, getting rid of 60% of your data or a very high amount. The caveats of this approach again is that building balanced models is hard, especially when you have not a lot of diversity. So you can't just you can do oversampling or boosting or whatever, but it will still be hard because you'll have a very small group of people in certain demographics. But this is why there's all these large data networks and federated learning approaches that you can use. The combinatorial explosion of analysis. Imagine just trying to do this over and over for a bunch of different phenotypes. So the general insights is that we found two very stable phenotypes. So this is dementia and Alzheimer's disease, but this is mostly because for those both models, the top predictive features are just a handful, and they're found on most patients. And this is where we're kind of going, and I'll talk about it later. The remaining three phenotypes is that show higher variation due to the fact that there are almost no dominant features between them. Thus, the models built in each experiment are considerably different. This is what happens when you have different groups of people, and their healthcare trajectories are different. So if we're talking about these features in commons, we see that dementia model on average, 7 out of the top 10 predictive features are the same. For Alzheimer's is 6. So those are the models that have the least variant. Why? Because those features were present in most races. Therefore, the model is able to separate them equally across, all the demographics. The frailty model, this has 2 out of 10 features, so there's not a lot in common. Mild cognitive impairment had 1, and Parkinson's had 1. So you see that there's a big difference here. And the big picture finding here is that, so we see that, is the main question, are the phenotyping algorithms fair for underrepresented minorities within older adults? Well, it depends on the phenotype. We've seen that for 2 phenotypes that didn't make a huge difference. For other three, it did. So, it depends on the underlying complexity, but sometimes it does have minimal effects. But it's good to quantify it because at least you will know, how to measure this and when is your model performing this way. Does it really depend on the phenotype? Well, we picked five phenotypes, that happen in older adults. So, however, we tried the same methodology on 16 other phenotype models, more general models that there are not necessarily, more general phenotypes that are not necessarily for older adults. Out of those 10 phenotypes, the performance varied widely. And we theorized that wide age ranges makes the performance change more. And six phenotypes are actually very consistent. So there's similar finding with the common features across the race spectrum. So how do we improve our models? This is a very common question. So a lot of people believe, oh, let's just tweak the model to get better overall performance. Why? Because the assumption is that a better model has less bias. Well, actually, no, and this is completely wrong. It actually increased bias when because you're mostly overfitting to the class that has a higher representation than your data set, mostly. You balance race distributions. Yes, this is one of the best approaches. However, it doesn't work for all models when there's no common features. So the features are more important. And also, not everybody has enough data for it. Should we use one model per race? Personally, I don't think so. But you need to, this is one of those things that you need to test in multiple different places. So how do we improve? So there's new exciting work where we tweak the features to get better models. And we're basically trying to find a common set of feature in the top 100 or top 1,000 set of for all models from the badly performing ones and anchor these models on these features. Meaning we're trying to make the machine learning build models around the features that are common, and this allows us to stabilize some of the older older adult phenotypes that we had in this work to less than 8% variance, which is kind of the sweet spot that we're looking at, and without any performance decrease. So this is, the kind of the future work, but we get to the point of showing that the phenotypes are biased sometimes, and we kind of did some work to show, how do we can tweak the features or the models in order to get on less bias or unbiased models. So acknowledgments. This has been work done with Dr. Vijay Ko and Dr. Nigam Shah and the Said Center at Stanford University, and this was funded by NIH National Institute on Aging Diversity Supplement. So if you have any questions, comments, you can feel free to reach out. Uh, we're looking for collaborators. We're looking for people to run the same methodology at their institution to be able to see if our theory is generalizes. Well, thank you very much for your time and have a good rest of your day.